In this video, we're going to start with some chemicals based on ammonia. And the first chemical that we will start with is nitric acid. This is a very old process and it involves three steps that starts with the catalytic combustion of ammonia to nitrous oxide, followed by the oxidation of nitrous oxide to nitric oxide, and finally the absorption of nitric oxide into water to form nitric acid. The catalytic combustion of ammonia with air to form nitrous oxide is actually one of the most efficient catalytic reactions with possible conversions up to 98% with very short reaction times. And the mixture of ammonia to water has to be below the explosion limit, which is 15.5% at 1 atmosphere. We can see here that the efficiency of the reaction has an optimum temperature around 900 degrees Celsius, and as expected, it's inversely proportional to the pressure, so it needs to be conducted at lower pressures. The catalyst used in this process is a platinum rhodium mesh. The biggest issue with that catalyst is that the process results in loss of these precious metals at high temperatures and pressures. That's why specific amounts of rhodium are added to decrease the loss of the catalyst. As you increase the amount of rhodium in the catalyst mesh, we can see a significant decrease in the loss for concentrations above 15% rhodium, accompanied with a significant improvement in the conversion efficiency as well. A further step to decrease the loss of the catalyst is using a recovery unit that is made of marble chips or platinum gold alloys to absorb the platinum oxide vapors and recover the lost platinum. The second step involves the oxidation of nitrous oxide to nitric oxide with oxygen. Before this step is conducted, the nitrous oxide stream has to be cooled. And this reaction is actually unusual because the reaction is quicker at lower temperatures and the reaction rate has a negative temperature coefficient. The last step involves the absorption of nitric oxide in water to form nitric acid. The reaction model for this step is quite complicated because it involves several components and several species of nitrogen oxides, including nitrous oxide, nitric oxide, and other species. So it's much more complicated. This is a flow diagram that describes a process which starts with pumping in a stream of ammonia that gets preheated, pressurized, and then pumped into the mixer. Another stream of air is pressurized and preheated, then pumped into the same mixer. The mixture of ammonia and air gets pumped into the reactor that contains a platinum rhodium catalytic converter, in which the first catalytic oxidation to nitrous oxide takes place. The stream of nitrous oxide goes through a second step oxidation and finally pumped into an absorption tower, in which an absorption into water takes place to produce the nitric acid product. The produced nitric acid can be concentrated up to like 68% in water, and this concentration is enough for most of the fertilizer production applications, but not for chemical nitration applications in organic transformations. There are other ways to overcome the azeotrope of nitric acid in water and get concentrations higher than 68%. And those include two main processes. The direct process includes the injection or absorption of nitric oxides into weak nitric acid under pressure. And the second indirect process includes the extractive distillation and rectification with sulfuric acid or magnesium. The largest use of nitric acid is in fertilizer production industry. The second largest in the manufacture of organic chemicals, which includes nitration steps. And the last category includes the production of explosives, metal nitrates, and nitrocellulose, and other nitrated compounds.